Welcome back. Let us look at applications of Laplace transform. Let us continue looking at applications of Laplace transform. What we have seen in the last video is how to solve a partial differential equation of first order with initial conditions, and we continue to do partial differential equations. Let us look at the second order differential equations, second order linear partial differential equation. The general second order linear partial differential equation you can classify into one of the three types, which is either hyperbolic, parabolic or elliptic. So you can second order term, that means the second derivatives you can always put it in one of the forms, either hyperbolic type, that is looks like a typical equation looks like a wave equation, and parabolic equation, typical equation looks like a hyperbolic heat equation, and then elliptic equation for which typical equation is a Laplace equation. So let us look into this. Any general second order a linear PDE, linear PDE. So let us how does it look? So you have some constant times a of x y times u x x plus b times u x y plus c times. So all a, b, c, d, all these coefficients are functions of x, y, u, y, y, and then plus d u x plus e u y, f u, and then is equal to some g, which is function of x, y. So this is the typical general equation. General equation looks like this. This, if you classify it based on b square minus 4ac, either it is 0 positive and is equal to 0 or negative. So depending on this you classify this equation into here hyperbolic, and then just this is as you see conics based on the motivated by the conics, similar to the conics. If this is positive, you can call them as hyperbolic type, and this is parabolic, and this is elliptic. So once you have this form, so once you choose this, you change this x y to new variable xi and eta. So there is a transformation involved, that is from x y to xi eta. So that is xi of x y and eta of x y. So xi equal to xi of x y, eta equal to eta of x y. Such a transformation if you use, or is the transformation from this variable to new variables. So what you have is in this case typical case, in the hyperbolic case what you get is u xi xi equal to u eta eta plus lower order terms, that is function of that's function of u xi, u eta, and u. Now u is a function of xi and eta, this is equal to 0. So this is how it looks, this typical hyperbolic equation. If you consider this equal to 0, this is exactly your wave equation. Okay, so typical equation, you can remove this, you get what you end up is this heat equation, this what is that, wave equation. So now you have in the parabolic case, when this is 0, you have a transformation from x y to xi eta. So that what you get is you can get this u xi xi or u eta eta equal to lower order terms, a function of u xi, u eta and u equal to 0. So typical equation here looks like, so this is the parabolic type of equation, this is the canonical form, and if you remove this, and then typical equation will be u eta, and this is your heat equation. Okay. So in this third case, this is similar to this hyperbolic case, only difference is xi and eta will be complex valued transformations. Okay. So if you again one more transformation you consider as a real part of psi and imaginary part of psi as new variable alpha beta, this will become u alpha alpha plus u beta beta plus lower order terms f of u alpha, u beta, u equal to 0. Now u is function of alpha beta. So alpha beta are real part of xi, beta is imaginary part of xi. So xi and eta are complex valued, xi equal to eta bar in that case. Okay, if they are complex, that is how you will get this. So in any case, a typical equation will be, so you remove this, so this is your typical equation, that is your Laplace equation. So the domain is basically in the plane. If you use xi eta variables, you have a plane alpha beta. So you have a plane, some region over which you have one of these equations is satisfied, and depending on its boundary, and you have to provide its your boundary data, or also if it is a heat equation, if it is eta, if you consider as the time that you call, if you give u at xi eta equal to 0, that is called initial value. Okay, initial value, initial condition. If you provide this, that is called initial condition. If you provide on the boundary, that is boundary condition. So you provide this, that you make it initial boundary value problems. You make a initial boundary value problem for one of these typical equations, and we will try to solve this by other techniques. We can solve by other techniques, but in this course we will solve by Laplace transform technique. Okay. So let me start with this first hyperbolic, that is a wave equation. So let me write directly what kind of so you have an example wave equation type. So before I do this wave equation, so let me solve some general equation. So if you cannot put, so you can put this in this form without putting canonical form, you may end up something like some typical equations, some simpler equations, even though they are like xy. So for example xy, here xy, if you have lower order terms rather functions of ux, uy, u equal to 0, this is actually a hyperbolic type. Okay. So you get u xi eta, and then once you have this is also another canonical form for, so these two are equivalent. So this one and this one, this you can go from this plus this. Okay. So rather these two are equivalent because this is also kind of hyperbolic. Okay. So let me give, if you are given equation in a simpler form like this with some known ux, uy, with simpler form for this f, you will let us see how we solve this hyperbolic type. So start with let me write as a hyperbolic equations. How do you solve this? Let me write the problem. So solve this u, x, t. X and t are independent variables, u is a dependent variable, and this is minus omega sin omega t, t is positive. So you need to apply Laplace transform. So I consider one of the variables as t. So t is this, and x is any full real line. So this is upper half plane is your domain, t positive, x belongs to full R. So this is what it is. This is x and this is t. So that is where in this upper half plane this is the equation is satisfied, and what you provide the data is you have a mixed derivative. So you have to provide u at initial data. So t variable t derivative is there. So you consider at t equal to 0 for all x, you make it equal to some x, that is the initial condition. This is the initial condition. Okay. And this is your boundary data. So let me provide boundary condition. So on this you have this, okay, x t equal to 0. So this is your initial data here, initial condition at t equal to 0. On the boundary u at 0 t equal to, let us say 0. So what is that boundary? X equal to 0, that is at x equal to 0 here, and then all along t, for all t you have this boundary. So on this we have these are the conditions you have got. Okay. So if this is your domain, initial condition is this, and you have a x derivative. Because of x derivative, let me provide a data u at x equal to 0. So x equal to 0 basically my domain should not be this full thing. So, otherwise this is not a domain. So, this is your domain. So, let us take this as x positive. So, then only this makes sense. So, then you see that this is one boundary and this is another boundary. So, on this boundary you provide a boundary condition. So, that is what is this, and this is your initial condition. Okay. So, how do we solve this? So, solution, simply as usual you apply Laplace transform for t variable, application of Laplace transform to the equation with respect to the t variable gives, what it gives is you apply this, you end up getting d. So, what you get is dou x of dou u by dou t, for which you apply the Laplace transform, that is s u bar of x s minus u at x 0. So, u at x 0 is x. So, let me use this as x, that is your left hand side, which is equal to minus omega, that is constant, sin omega t, that we know that this is actually omega divided by s square plus omega square, that is the Laplace transform of sin omega t. So, here x is still positive, and then you consider this. So, you have s dou u bar of x s by dou x minus 1, and that is going to be this side. If you bring it, that is going to be here. So, we have 1 minus omega square by s square plus omega square. This is s square by s square plus omega square. If you just square plus omega square minus omega square, simplify this, you get this. So, s cancel both sides. So, you end up getting dou u bar by dou x equal to s divided by s square plus omega square. So, you apply this, if you solve this and use this boundary condition. Boundary condition is, if you apply boundary condition, since the boundary condition is, since u at 0 t is 0, u bar of 0 s is also 0, because for which you can take Laplace transform, and this is this. So, you solve this equation with this condition at x equal to 0. So, you get u bar of x s is simply integral of this. So, that is x s by s square plus omega square, that is constant, and you have x plus some constant. Okay. So, where c is constant. You apply this condition, boundary condition, that makes it 0, which is u bar of 0 s. So, this is typically is c. If you put x equal to 0, this is 0 and you have c. So, c is 0, that means c is 0. So, that implies u bar of x s. The solution is s x by s square plus omega square. Now, you consider its inverse transform. Inverse transform gives the solution u of x t is equal to x times, you are doing with respect to is s, right. S divided by s square plus omega square is cos omega t is your solution, is your inverse transform. So, this is your typical solution. This is your solution for x positive and t positive. So, this is your solution. You can also consider now this way. So, separately you can also consider this way. This is as though this is your domain. You can also consider as t equal to, so this initial condition you can consider also here and here separately, you get the same equation. So, eventually if you consider that problem, you will get that that is also valid, same solution you will get for this t positive x negative. So, you consider the domain as left hand side. For example, this one, this is your domain, this is your t and this is your x, x is my 0, and you have an initial condition here, and this is your boundary condition, you have a PD here. And then if you do, this is your domain, within this domain you see that you will get the same solution, there is no change. So, you end up getting, so the final solution, so you can write both the cases. If I remove that x belongs to R, you can, what I worked with is initially x positive side, x negative side also you can get, similarly we get x negative side implies u of x t is x cos omega t for every x belongs to R and t positive. So, this is your solution. Okay. So, let us look at another example. This in this case we will try to solve some wave equation. Let us consider a wave equation for transverse vibration of a semi infinite string. I consider some semi infinite string, this is 0 to infinity. Okay. If I have initially this string is at rest, that means u at x 0 is 0, u t at x 0 is its velocity and its displacement both are 0 initially at rest at t equal to 0. And what I do is here I provide some boundary conditions. So, some boundary conditions, if I provide u at x, that is x at 0. So, u at 0 t, I give you some function of x, function of t at this point, and you assume that if you do that, and what happens at infinity, you do not have any displacement, because whatever you are giving here it is going to be propagating, because your equation is wave equation. So, u has to go to 0 as x goes to infinity, okay, for all times. So, that is at infinity. So, those are the two boundary conditions, these are the initial conditions. So, how do we put this as a boundary value problem? So, because of this, this is transverse vibrations in a semi infinite string. So, you have a wave equation is satisfied. So, u t t equal to c square u x x, x is positive and t is also positive. So, this is your domain. So, if you look at this way, this is your t, so this is your domain. Semi quarter plane you have this is a domain, and you have initial data, initial conditions are u at x 0 is 0, u at dou u by dou t at x 0 is 0, and you have the boundary conditions, those are u at 0 t, let me give as some constant times f of t. Okay, so, let me give only f of t, okay, f of t, and then u of x t goes to 0 as x goes to infinity. So, this is the boundary conditions. So, this is your problem. So, let me solve this, this is a wave equation, non-homogeneous wave equation, this is wave equation. So, wave equation, so or rather how do we put it, vibrations of transverse vibrations of a semi infinite string. So, this is a typical boundary value problem for this vibration. If you want to look at the vibrations or the displacement in the string, and you have provided at this end, disturbance you provide at this end, otherwise which is at rest initially. You disturb it at this end all the time with the f of t. As time progresses, you have f of t. At time t, you give a disturbance of f of t, how it propagates all along this as a displacement in the string. So, the solution as usual, it's because it's in the quarter plane problem, we apply Laplace transform. Laplace transform gives the equation becomes, what is this equation becoming, you apply this here, u t t, if you apply s square u bar of x s with respect to t, okay, with respect to t gives this s square u bar minus u bar at u at x 0 minus s times this, and u here dou u by dou t at x comma 0. So, this is your u t t, this is equal to c square. If you apply this here, simply dou square u bar of x s by dou x square. So, u of x 0, this is 0, and this is also 0. So, these are by initial conditions. Use the initial conditions to make this 0. So, this implies dou square u bar by dou x square minus s square by c square. I divide with c square because c is non-zero, which is the speed of wave. Okay. C square is positive or c is non-zero, times u bar, which is equal to 0. And you have this boundary conditions will provide u at u bar at 0 comma s, if you, that is equal to f bar of s. For a Laplace transform of this, if you consider, that is u bar of 0 s, which is equal to f bar of s. And then u here, this becomes u bar of x s goes to 0 as x goes to infinity. So, these are the, this is the problem now. This becomes ordinary differential equation here. The domain is x positive, s is something which you do not know, still s is for a, s is a Laplace transform variable, there is a complex variable, and you have this. So, how do we solve this? You solve this ODE, but typically you have a solution of this is u bar of x s as this is m. So, if you use a complementary, this is like y double dash minus a square y equal to 0. So, y of x is e power a x plus c1 times this, c2 times e power minus a x. So, that is your solution. So, if you use this same thing here, you have c1 times, because this is the derivative. So, you have c1 of this is a constant. So, this is c1 times some constant times e power a is s by c times x plus c2 times e power minus s by c times x. Now, apply this initial conditions and then if you apply this initial condition, let us see, if you apply first the last one, as x goes to infinity, this has to go to 0. That is possible only if c1 equal to 0. Okay. So, this implies c1 has to be c1 has to be function of s. Okay. So, in any case, so let us use since u bar has to go to 0 as x goes to infinity, we must have c1 equal to 0. So, this gets cancelled. So, the general solution is only this one. Now, you apply the first initial condition, that is u bar of 0 s, that is f bar of s, which is u bar of 0 s, which is here, from here you have c2 times we put x equal to 0, that is c2. So, this implies u bar of x s. Now, I know what is my c2, that is f bar of s times e power minus s x by c, x positive. So, you can invert now. So, inversion now gives the solution u of x t, which is equal to, so what is its solution, and you have already seen that earlier e power minus a s times Laplace transform of f of t. I am using this property, which is equal to Laplace transform of f of t minus a times h of t minus a. Okay. So, this makes L inverse here, L inverse of this is equal to this. Okay. So, here we need L inverse of e power minus a is s by c times x, x by c is your a times s, Laplace transform of f of t. So, if you use this property, you end up getting f of t minus x by c times Heaviside function of t minus x by c. So, if you write this, you get if you write the definition of the Heaviside function, you end up getting, if t is less than x c, that is 0. So, you have 0 if t is less than x by c. If t is greater than or equal to t x by c, you get f of t minus x by c. So, this is your solution of your boundary value problem. So, this is how it behaves, this is your solution. So, this is how you get the vibrations as that is x is less than, or x you can put it this, x is less than t times c. As time progresses less than this, you will always find this non-zero. So, as you see, after some time t times multiplied with this, up to that point you have the disturbance. It propagates with the speed c for time up to time t, tc times. Tc is, this shows that t times, this is the velocity, that is x by c, x by t, the tt goes with some kind of distance. Okay. So, this is a distance up to which you have the disturbance that is travelling. Okay. So, you solve this. So, this is how you solve a wave equation. A wave equation or hyperbolic type equation, simpler equations with initial and boundary conditions. You can make use of them and use the Laplace transform to solve the, find the solution of this boundary, initial boundary value problems. Let us look at one more example. One more example of wave equation. So, let us solve. So, this is about inhomogeneous or non-homogeneous wave equation. How do you solve this? So, problem is about solving. So, solve this problem. So, you have u t t equal to c square u x x, again x is between, so this is u minus of this is equal to, I give you some constant times k times sin pi x by a. So, this is a kind of forcing. Okay. So, outside force is this. So, this you have typically I give between 0, domain is a strip, let us say a t positive. So, you have only strip here. So, you have a strip that is 0 to, or rather let me write this way. So, if you have this is x and this is t, so you have this strip. So, your equation is valid here. Okay. T is positive. So, you have only up to here. So, this is your strip. So, these are your boundaries. So, let me provide the boundary data, that is initial conditions at t equal to 0 I have to provide, because you have a this is your boundary. So, at this t equal to 0, so you have to provide boundary. So, let us say it is at rest. So, you have a string of length a, okay, which is at rest, initially. So, u at x 0 equal to 0 and dou u by dou t of at x equal to 0, x 0, t equal to 0, this is 0. These are your initial conditions. A boundary is, these are the two boundary conditions, that is at x equal to 0 and x equal to a, these two. Okay. So, u at 0 t for all times I provide, this is also 0, let me use this also 0, u at a t is also 0. So, let us attach the string which I fix it, whose displacement is 0. So, I fix these ends so that you have these boundary conditions. And only thing is, because of this forcing, outside force, how this string is how this behaves, string is behaving, how this string gets the vibrations in this string. Okay, we will see how it is by looking at these solutions. So, what we do is, again because t is a variable, that is typically, so c is here a speed of wave, c is the speed and k is constant, k and a are constants. Okay. So, solution will be, so as usual t is positive, t is valid for all 0 to infinity, you can apply Laplace transform to t variable. Laplace transform to the t variable gives, what you get is again, so you have s square u bar of x s minus s times u at x 0 minus u dou u by dou t at x 0. So, both are 0 from this initial conditions. So, 0 minus c square dou square u bar of x s divided by dou x square is equal to k times sine of sin pi ways, this is a constant I am doing with respect to t. So sin pi x by a times k is a constant comes out. So, it is only Laplace transform of 1, that is 1 by s. I use the initial condition. So, you finally get dou square u bar by dou x square, you divide with c. So, you have you bring it to the other side, and then so you have a minus s square by c square u bar is equal to, bring it, so and bring this one to this side. So, you have minus k by s and k by s c square sin pi x by a. So, this is your solution between 0 x to a, and you have a boundary data. So, that you can have now u bar at 0 s is 0 and also u bar at a s is also 0 from the boundary conditions. If you use the apply the Laplace transform to these two boundary conditions, you get this. So, this is the problem you have to solve, and finally, before you take the inverse transform. So, what is its solution? So, solution is so u bar of x s, if you solve this ordinary differential equation, complementary function is m square minus s square by c square equal to 0. So, m equal to plus or minus s by c. So, your typical solution is looking like c1 times e power s by c x plus c2 times e power minus s by c times x, then plus a particular integral. So, this is this particular integral you can get it, because if you have a sign, you write the equation as a d square minus s square by c square operating on u equal to some constant times whatever. If you have a sin ax, then what happens, the particular solution is up is 1 over wherever d is there, you put minus a whole square minus s square by c square. This is your particular solution, of course with sin ax. So, this is a usual way to get operator form. So, this is the shortcut way to find the solution, particular solution, if you are familiar with the differential equations, or otherwise you look for a particular solution of the form yp of here up of x, up bar of xs, you look for something like a times sin pi x by a plus b times cos x pi by a. If you look for and substitute into the equation, and you can get your a and b, so that you see that a will be this one. Okay. You will end up getting b equal to 0, and you finally get what is this value. This value you will see that is going to be something like this. Okay. Of course, for this you have this. So, if here I have minus k divided by s c square times, and this you have a sin ax by this minus plus, and here you get s square plus c square a square. C square goes up, so you have c square cancels. Okay. So, this is how you get this. So, let me remove this, this is what you get. Now, this is x positive, this is your solution. Now, I have not applied this initial boundary conditions, these conditions. So, if you use these conditions, u bar at 0 s equal to 0, that is c1 plus c2 sin ax, that is 0. So, c1 equal to minus c2, and what happens to other solution, u bar at as, that is c1 plus c1 times e power s by ca plus c2 times e power minus s by ca plus k by s times sin a square, which is constant. So, s square plus c square a square. So, if c1 equal to c2, if you put it here, so you see that c1 equal to minus c2. So, if this has to be, so if you solve this two, you see that you consider these two equations, this is one equation, this is another equation. You try to solve for c1 and c2, you end up getting you may not have any solution at all. Okay. This is inconsistent, c1 plus c2 cannot be same as you may get determinant is non-zero. Oh, I think I made small mistakes here. This is not ax, this is k by this is pi x by a. So, k by s c square, this is actually, you start with looking at this is a particular solution, let me write, I have written wrongly, s c square sin pi x by a and s square by minus. So, you have here this is going to be a square, a is pi by a here, pi square by a square plus s square by c square. That is exactly what you have, because here a this a is reference. So, what you have is pi by a is your constant. So, pi by a whole square plus s square by c square. So, here you have c square a square comes out, okay, or rather multiply c square if you remove it. So, you can write here c square and you remove this here. So, this is 1, and if you now use this sin, it's a sin pi a by a, that is 1. So, sin pi. So, this is 0 because of this, and you can see that C1 has to be, C2 has to be 0. Okay. If you do not have this sin pi x by a pi, and then you will end up getting C1 C2 something, for which then you will have to worry about how do you invert it. Okay. You can also do that, it is a little complicated. Okay. Instead of sin pi x by a, if you take sin x by a, then you have sin 1 you will get. So, this is a non-constant, you will end up some constants, you will be able to solve by solving these two equations, you can get your C1 and C2 and you put it here, and now you have to invert it, that is so you should know what exactly that Laplace inversion of e power a s. Okay. But this is actually Laplace is so some heavy side function of t minus a or something you will get. Okay. T plus a, whatever you get. So, you can use that and get this. So, you can use let me use because I choose this pi x by a. So, things are simplified here. So, if you use this, you have C1 C2 both are 0, because if you put C1 equal to minus C2 here. So, if you put minus C2, so you end up getting, if you put it here, so C1 and then e power s by Ca, and this C1 e power minus s by Ca. And because I put C2 equal to C1 minus C1 by the first equation. So, C1 is common, has to be 0. This cannot be 0. So, this implies C1 equal to 0. Once C1 is 0, C2 is 0 from the first equation. So, this implies C1, C2 both are 0. So, that means your solution of that equation is of x is minus k by s. Of course, this becomes plus. Okay. When you apply this minus and that minus becomes plus, I missed it. So, k by s sin pi x by a divided by pi s square plus pi c by a whole square. So, for which this is your x positive, and you can invert it now. Inversion gives, Laplace inversion gives u comma x comma t. This is your solution. Now, this is k sin pi x by a, that is nothing to do with s variable. You have Laplace inversion of this, you can write 1 over s times s square plus pi c by a whole square. Okay. This you do the partial fractions here. If you use the partial fractions, k times sin pi x by a times L inversion of 1 by s, let us say minus 1 by s square plus pi c by a whole square. So, this one minus s if I do, so you end up getting this whole thing into, you get pi c square by a square. So, if you multiply here a square by pi square c square, if you do, then this is same as this one. Okay. So, you have k a square by pi square c square sin pi x by a. The Laplace inversion of 1 by e is 1 by s is 1, and then remaining this is cos pi c by a t. Okay. So, this is exactly the solution you are looking for x positive and t positive. So, this is the solution. So, if you have a string of finite thing which is fixed at both ends and initially at rest, and by that external force, that force is maybe wind or something, but it is in this form. for all at every point x you have that much pressure on the string, then for all times if you keep that thing, the string vibrates in this fashion. Okay. So, this is how you solve this wave equation or hyperbolic equation with initial boundary conditions. Okay. If you have a wave equation or hyperbolic, any hyperbolic type of equation with initial boundary conditions, you can apply Laplace transform and finally inverting it, use all these initial and boundary conditions, you get your u bar of xs, and finally you invert this to get your solution u of xt. Okay. So, this is how we solve these typical hyperbolic equations. Similar such equations can be solved, but it's there is a limitation, not all boundary conditions, all boundary value problems you can solve for this any equation, rather not just hyperbolic, even other equations, not all equations, not all boundary value problems you can solve by this technique. Certain simpler some equations which you cannot solve by other which are difficult to solve by other methods, the Laplace transform will give you nice easy solution. So, it has its limitations. The only limitation is you may end up getting u bar of xs as something little complicated, and for which if you to find the inversion you may not get that easily. So, you have to apply your contour integration technique to find that Laplace inversion and finally to see its explicit solution. So, in principle you can apply this Laplace transform and its inversion to get the solution for this boundary value problems, initial and boundary value problems for these hyperbolic type equations. Okay. We will see next in the next video we will see how to solve heat equation with the initial and boundary conditions. In different problems we will try to work out using Laplace transform. We will see next video. Thank you so much.